You can wear the helmet, and that means you can move your head while the scan's happening, and that's great, especially for children who really struggle to sit still for any length of time.
Fellow Homo sapiens, my name is Torie Robinson, and welcome back to Epilepsy Sparks Insights. In part 2 of 2 this week about OPM-MEG brain scans, check out part 1 with Christina Embury last week if you haven't yet seen it, we have guest star researcher, also from Young Epilepsy, Zelekha Seedat, who will elaborate further for us on the research that they are doing into childhood epilepsy and indeed how clinicians and patients and really their families can be involved.
So I'm a postdoctoral researcher and trainee physiologist at Young Epilepsy. So I originally did my degree and my PhD at Nottingham, at the University of Nottingham, and that was in MEG, so the physics of MEG, and then also applying machine learning algorithms to MEG data to look at healthy brain activity, but also activity from kids with epilepsy.
And could you just confirm for those who aren't familiar, what is an MEG? Because most people have heard of EEG, MRI, etc., but what does MEG stand for?
So MEG stands for Magnetoencephalography, and it means that we're measuring the tiny magnetic fields produced by your brain. So in EEG, you're measuring the electric fields produced by your brain. In MEG, you're measuring the magnetic fields. And the difference is that the magnetic fields pass straight through the skull, which means that you can then pinpoint where that activity is coming from. Whereas in EEG, the electric fields get sort of smeared out by the presence of the skull, which is not a good electrical conductor. And that means you can't really tell where that activity is coming from, except to say, it's coming from the left frontal lobe, rather than, within millimeter accuracy, this is where it's coming from.
And compared to an MRI?
So MRI measures structural brain, like what the brain looks like, essentially. Whereas MEG and EEG measure brain function, so what the brain is doing, so the activity that's passing from one part of the brain to another part of the brain, rather than what it looks like. So
we have that, relatively new, right? Fancy opium, which I really like saying because I'm so mature. But tell us what the OPM-MEG is.
So OPM. Yeah, Optically Pumped Magnetometers. So all they are tiny little sensors that can measure these magnetic fields from your brain. But the difference is that they measure it using a combination of like a little cell of gases and lasers. So it uses lasers to work, essentially. So there are different magnetic field sensors that have been used to measure MEG in the past. But the OPMs use lasers to work. It means they can be smaller and they can be placed on the head. They don't need to be kept in a big vat of liquid helium.
I've seen pictures of OPM-MEGs and they look quite bulky. There's loads of wires everywhere. Can you tell us the pros and cons, please, of using, and look at the complexities of the OPM-MEGs, please?
Yeah, so one of the good things about OPM-MEG compared to cryogenic MEG is that it's wearable. So the sensors, like I said, they don't need to be kept really cold in a big vat of liquid helium. They can just be mounted in a bike helmet kind of thing on the head. So it's just like a 3D printed lattice structure.
And the way that you hold it, it looks quite light.
Yeah, it is. I mean, it doesn't really weigh a lot. Once you've got all the sensors in it, it's a little bit heavier, maybe sort of a kilo. So it's quite heavy to have on your head. For adults, it's completely fine. We can comfortably scan like a 4-year-old child with it on for a while. But any younger than that, and I think they do start to feel the weight, they get a little bit uncomfortable and maybe they'll rest their head on the back of the chair. So this is not the final solution. So there are lots of things we're still trying to work out. OPM-MEG is a brand new technology. So we're still trying to work out the best way to mount them in a helmet or in a flexible cap or different things like that. The sensors themselves are changing all the time. The cables from the sensors to the electronics change. The electronics themselves change. So bits are changing all the time and none of it is the final solution just yet. So trying to record MEG in a system that's brand new but also changing is really quite difficult, and to interpret it and to know exactly what you're looking at. So for example, you can, like I said, you can wear the helmet and that means you can move your head while the scan's happening, and that's great, especially for children who really struggle to sit still for any length of time. They can be wearing their helmet, they can be watching Bluey, their favourite TV programme, anything they want to watch. They can just chill, they can watch whatever they want to watch, or we can be doing MEG tasks with them. And while they're doing that, they're moving their heads ever so slightly. So the cables will be moving behind them.
Yeah.
So we can get things like cable artifact, but also they're moving their heads through a magnetic field, which also produces an artifact. And none of this is recorded in EEG or in cryogenic MEG. So we need to be able to recognize those artifacts and also with confidence understand exactly what we're recording from the OPM-MEG.
That does sound rather complex and challenging.
Yeah,
so
it is.
How are you going to learn how to do that and I guess interpret the data and to get what we need?
Yeah, so our solution is to record EEG and OPM-MEG at the same time. So clinicians and physiologists working in the field of like epilepsy imaging, I guess, are used to looking at EEG. Mm-hmm. And that means that that's the space that they're comfortable with. That's how they're trained. So if we record EEG, so we stick all the wires on like normal and then put the OPM-MEG helmet on top and then record them both at the same time, we can use the EEG as kind of a roadmap to help us understand what we're looking at in the OPM-MEG. So if we see some like epileptiform activity in the EEG, then we can look in the OPM-MEG and say, well, okay, this is exactly what it looks like. These are the similarities and differences. And then similarly, if we have like weird cable artifact at the back of the head and we want to know if that's genuine brain activity or just cable artifact.
Like a wiggle.
Yeah, exactly. We can look in the EEG and see, is that wiggle brain activity or is it just the cables moving? And then being able to share that with doctors and say, we're confident that what we're looking at is this, or we're confident that actually it's artifact. So that's our solution, is to record them both at the same time to start with.
So you'll be able to identify correlations between both sets of data to clarify what is real and useful and what is just like a wiggle in the background. Yeah,
exactly. And, we can have all the fanciest, newest, cutting edge brain technology in the world. But if there isn't a clinician who understands how to use that data or a training pathway to upskill clinicians and physiologists to be able to record and interpret that data, then it's never going to be used. Like, we need the workforce to be in place alongside the new cutting edge technology as well.
When does your study finish, actually, this particular study?
So we've got another couple of years. And so the study that we're doing at the moment, we are recruiting children with focal epilepsies who are candidates for epilepsy surgery.
So not generalised, must be focal.
Focal, yeah. So that's one part of the study. And then we've got another part of the study, which is actually anybody that comes to young epilepsy to have like a clinical EEG. So they could have generalised seizures.
Anybody meaning children, sorry.
Yeah, children. So at Young Epilepsy, we see kids and young adults up to the age of 25. So for some of those patients, we're recruiting them to be recorded in the OPM-MEG as well. And that's because we want to understand at a population level, like, who this study is useful for. So we already know that it's probably useful for surgical candidates, but for other people, a lot of kids have like sensory challenges or other extra complicated needs. They really struggle to sit still and have an EEG put on their head. And if we could show that OPM-MEG shows you exactly the same thing as EEG, plus a little bit more, and it's less difficult to do because you can just put a hat on them, then that could be really valuable for some of those patients. So it's trying to work out exactly the patient populations that will benefit from it now and in the long run as well.
I imagine if we can find out that it benefits kids, those kids will grow up and it could benefit them in the future too.
Yeah.
So it sounds quite exciting. And I believe it's all like silky in the middle as well, isn't it? So it's not like rough on your face. Because stereotypically, if you have an EEG, you've got the grit, right? Which goes in your face and the glue and stuff like that. And lots of people hate that, right? And so I imagine this device, you don't have to go through any of that because it's all slippy and you just plonk it on, right?
Yeah. So we've actually got like a wool insert. So the sensors, the OPMs get a little bit warm. So we have like a wool insert, like a little hat that goes underneath the helmet. So it's nice and soft. Obviously, some of the people we're also recording EEG at the same time. So right now we're still using the paste and the grit. But for kids who aren't having EEG at the same time, then yeah, it's just a comfy, warm hat.
But for this study, they will be having both at the same time. But it's like, 2 in 1, I guess. And it's
and it will help us for the future as well. I mean, I don't think we should be aiming to always do EEG and OPM-MEG at the same time. It's just for the next few years to help us build up that database of this is what OPM-MEG data looks like, and we can confidently interpret it. So in 10 years time, I don't know, we might not need to do EEG and OPM-MEG together.
Oh, interesting. Where do you think we'll be in 10 years time?
Oh, that's such a question.
Isn't it? It's like a question from Telly. So tell us about the future.
Yeah. I'd hope that we've moved so at the moment we're definitely a research system. I would hope that there would be an OPM-MEG system somewhere in the world that is clinically approved. So it's gone through the medical device approval and somebody has said, yes, it does what it says on the tin and it's safe and you can put it in any hospital. So I'm hoping in 10 years time that commercially available medical device approved systems will start to appear in hospitals so that we can use it in the clinic rather than just for research. That's where I hope we'll be.
And then hopefully as a result of that, we can collect more data simultaneously. People need to spend less time in the hospital and get the results that we need earlier to get people in surgery earlier if they need it, right? Which could potentially reduce the number of people who have like cognitive regression or, insults to the brain as a result of the seizures. And instead, gosh, I'm promoting it already. But yeah. For everyone listening and watching, we have the study on the Epilepsy Sparks page for research that you can check out. And if you can propose that to either your patients or to your clinicians, and hopefully we'll get more people on this cool study.
Thanks so much.
Thank you so much to Zelekha for elaborating on what an OPM-MEG is, for reconfirming that it has nothing to do with opium, and for getting us all excited about and sharing how families and clinicians can get involved too. Check out Zelekha's papers and more about her work via the website torierobinson.com, where you can also access the podcast, the video and the transcription of this entire episode. And if you haven't already, don't forget to like, comment and subscribe to our channel and share this episode with your friends, your colleagues, your family members, and see you next week.